You think you understand reality. You wake up, you touch the table is there. You close your eyes, the table is still there. That is the deal we made with the universe since the day we started thinking. Things exist. Things have locations. Things have properties, whether you look at them or not. That is the deal. Quantum mechanics broke that deal. Not philosophically, not as a metaphor, not as a thought experiment that physicists argue about over coffee. Experimentally. With lasers, with superconducting circuits, with single electrons fired one at a time through a gap the width of a human hair. The math predicted it. The labs confirmed it. More than 1 million experimental trials in a single study have shown that the universe does not work the way your brain says it should. And the strangest part, the part that keeps physicists up at night in 2025, the centenary year of quantum mechanics, is that after 100 years of evidence, nobody fully agrees on what it means. Not what it means philosophically. What it means about what is actually out there. That is the shadow the title is talking about. Not a metaphor for doubt. Literal shadows cast by quantum behavior onto the concept of an objective, observer-independent reality. If you value documented, deeply researched science like this, subscribe right now. It is the best way to support the work. And drop a comment telling us which city you're hearing this from. Also, before we go further, 2 of the main sources anchoring what you are about to hear are the Physical Review Letters journal entry from the Delft University team published in October 2015, documenting the first loophole-free Bell inequality violation using electron spins separated by 1.3 kilometers, and the MIT news release from July 2025 covering the most idealized double-slit experiment ever performed, with atoms used as the smallest possible slits. These are not Wikipedia summaries. These are primary experimental records. Now back to the story. It starts in 1801. A British polymath named Thomas Young, working in London, shines light through a card with 2 tiny slits. He expects 2 bright bands on the far wall. What he gets is a zebra stripe. Light and dark bands, dozens of them, spreading across the wall like ripples from 2 stones dropped in a pond at the same time. Young has just proven that light behaves as a wave. Waves from the 2 slits overlap, reinforce each other at some points, cancel each other at others. The stripes are where they add up. The dark gaps are where they cancel. Wave interference. Simple. For 100 years, that is the answer. Light is a wave. Done. Then, in 1905, Albert Einstein notices something Young missed. When certain metals are struck by light, electrons get knocked out. But the energy of those electrons does not depend on how bright the light is. It depends on the color, meaning the frequency. Einstein concludes that light comes in individual packets of energy. He calls them quanta. Later, they get the name photons. Einstein wins the Nobel Prize in Physics in 1921, specifically for this discovery. Not for relativity, for proving light is a particle. So which is it? Wave or particle? Young showed wave, Einstein showed particle. The answer, delivered by quantum mechanics in the 1920s, is both, and that answer is still the most disturbing thing in all of science. Here is where it gets sharp. In the 1980s and 90s, the double-slit experiment gets refined to the level of single particles. Not beams, 1 electron at a time. You fire electrons, individually, toward a barrier with 2 slits. You do not know which slit each electron goes through. You record where each one lands on the detector screen behind. After enough electrons, you step back and look at the pattern. Stripes. Still stripes. A single electron, fired alone with nothing else in the apparatus, produces an interference pattern as if it went through both slits simultaneously, as if one particle traveled 2 paths at once, interfered with itself, and chose a landing spot based on the probability wave that resulted. That is not a theory. That is what the detector shows every time. And then the physicists ask the obvious follow-up. Which slit did it actually go through? They install detectors at the slits, a tiny instrument designed to register a photon or an electron as it passes through. Now they can catch each particle in the act. Now they will know. The interference pattern disappears. Not weakens? Disappears? When the detectors are on and the path is known, the electrons land in 2 broad bands, exactly where you would expect. If they were particles going through one slit or the other, wave behavior gone, particle behavior restored. The act of measuring which path the electron took changed what the electron did. And this is not a matter of the detector disturbing the electron in some clumsy mechanical way. The mathematics of quantum mechanics shows this as a fundamental feature. Information about the path destroys the wave nature. Gaining knowledge about which way the particle went eliminates the possibility of interference. Heisenberg had already formalized this in 1927. His uncertainty principle states that you cannot know both the precise position and the precise momentum of a particle at the same time. The more precisely you pin down one, the more uncertain the other becomes. This is not a limitation of your instruments. It is baked into reality. The uncertainty is in the particle itself. Werner Heisenberg, working in Copenhagen under Niels Bohr, wrote after winning the Nobel Prize in Physics in 1932, "What we observe is not nature itself, but nature exposed to our method of questioning." That line sat in journals for decades. Physicists debated whether it was poetry or physics. The Bell tests answered it: physics. Back in 1927, at the famous Solvay conference in Brussels, Belgium, Einstein refused to accept this. He proposed a thought experiment to Bohr. A photon passes through the double slit. The slit itself is mounted on a spring. When the photon passes through, it gives the slit a tiny kick, like a bird brushing a leaf. Measure that kick precisely enough, and you know which slit the photon went through while still seeing the interference pattern. Particle path and wave interference at the same time. Einstein believed this would break the uncertainty principle. Bohr thought about it overnight and came back with the refutation. The uncertainty principle applies to the measuring slit, too. If you make the slit free enough to detect the kick, its own position becomes uncertain. That uncertainty washes out the interference fringes. The measurement and the pattern cannot coexist. Einstein lost that argument, but he never accepted it. For nearly 100 years, nobody had the technology to actually run Einstein's proposed test. In 2025, physicist Jianwei Pan at the University of Science and Technology of China finally did it. Pan's team trapped a single atom using an optical tweezer, essentially a focused laser beam acting like tweezers made of light. They used that atom as the slit. When a photon struck the atom recoiled, just as Einstein had imagined. By tuning the depth of the optical trap, Pan's team could control how precisely they could read the recoil. Sharper recoil information meant better knowledge of the photon's path. And every time the path information sharpened, the interference fringes on the detector screen faded until they nearly vanished entirely. Bohr was right. The study was published in Physical Review Letters. The 100-year argument between Einstein and Bohr was resolved by data in 2025. But resolving that argument only opens a bigger one. If measurement changes outcomes at the quantum level, what counts as a measurement? Does it have to be a human, a machine, any physical interaction at all? In July 2025, the MIT News Office reported on the most idealized version of the double-slit experiment ever performed, led by Wolfgang Ketterle, a Nobel Prize winner, and his team including physicist Vladan Vuletic. They used atoms trapped in an optical lattice, a grid of laser beams, as their double slit. These were ultra-cold atoms, chilled to temperatures near absolute zero, forming what is called a Mott insulator, a quantum state where atoms sit rigidly spaced. Then they released the atoms from the trap and hit them with a single photon. The photon scattered off two adjacent atoms the same way light scatters off two adjacent slits. The team's conclusion, stated explicitly in the publication, was that what matters is not the spring-like laser holding the atoms in place, but the fuzziness, the quantum uncertainty of the atoms themselves. The quantum correlation between the photon and the atom determines whether you get a wave or a particle, not the apparatus. The quantum entanglement between the measured system and the measuring system, that word entanglement, is where this gets truly unsettling. Entanglement is what Einstein called spooky action at a distance. He used that phrase dismissively in a 1935 paper he co-wrote with Boris Podolsky and Nathan Rosen, published in the journal Physical Review. The paper, known by the initials EPR, argued that quantum mechanics must be incomplete. Two particles can be created together such that their properties are correlated. Measure one, and you instantly know something about the other, no matter how far apart they are. EPR argued this correlation had to come from some hidden information carried within the particles from the moment of their creation, what are called local hidden variables. The particles were not actually uncertain. They just had preset values we could not see. Einstein, Podolsky, and Rosen thought this was an obvious point. They thought they had caught quantum mechanics in a contradiction. They were wrong. In 1964, Irish physicist John Stuart Bell published one of the most important papers in the history of science. He showed that if local hidden variables existed, the correlations between measurements on entangled particles would obey certain mathematical bounds. He called these bounds Bell inequalities. If experiments violated those bounds, hidden variables were out. The universe truly was as weird as quantum mechanics claimed. It took decades to build the experiments precise enough to test Bell's theorem without loopholes. The first truly loophole-free test came in 2015 at Delft University of Technology in the Netherlands, led by Ronald Hansen. His team entangled electron spins in diamonds separated by 1.3 kilometers. They performed 245 trials. The result was an S-value of 2.42, plus or minus 0.20. Bell's inequality says S cannot exceed 2 if local hidden variables are real. The probability that a local realist model could produce this result by chance was at most 0.039. That is not quite 3.9% chance of being a fluke. The result was statistically significant rejection of local realism. The paper appeared in Nature in October 2015. In 2023, a team at ETH Zurich in Switzerland ran an even cleaner version using superconducting circuit qubits, connected by a cryogenic link spanning 30 meters. They evaluated more than 1 million experimental trials. Their average S value was 2.0747, with a margin of error of plus or minus 0.0033. The probability that local realism could explain their results was smaller than 10 to the power of negative 108. That is a number so small, it has essentially no meaning in daily life. The paper was published in Nature. Local hidden variables are not a viable explanation for quantum entanglement. The universe is non-local. This means two particles can be correlated in ways that cannot be explained by any information they carried from the start. Measuring one particle instantly affects what we find when we measure the other, regardless of distance. No signal passes between them. They are simply part of the same quantum state that does not collapse into definite values until a measurement is made. Definite values until a measurement. There it is again, the measurement problem. Here is where we need to pause, because this is where quantum mechanics splits into different camps, each of which has serious physicists defending it, and none of which is experimentally proven wrong. The first interpretation is called Copenhagen. Formulated by Niels Bohr and Werner Heisenberg in the 1920s, it says, the quantum wave function describes all possible states a particle can be in. When you measure it, the wave function collapses to a single definite value. Before measurement, questions about which specific state the particle is in are simply not meaningful. Reality does not have a definite state until observed. Copenhagen is the most widely taught interpretation in physics courses worldwide. The problem with Copenhagen is that it never clearly defines what counts as an observation or a measurement. Is it a detector, a human eye, any physical interaction at all? The mathematics does not say. Bohr himself, when pressed on this, said that the boundary between observer and system is not fixed, but can be placed anywhere, and the physics will not change. That sounds like a practical workaround. And for 80 years it was. But it is not an answer to the metaphysical question. Copenhagen is famously described as shut up and calculate. Use the math, get the predictions, stop asking what is really happening. For most working physicists, that has been enough. The transistor in your phone does not care which interpretation is correct, but reality does, if reality exists the way we assume it does. The second interpretation is many worlds, proposed by Hugh Everett III in 1957 in a Princeton doctoral thesis. Everett's idea: the wave function never collapses. Instead, at every measurement, the universe branches. Both outcomes happen. In one branch, the electron went through the left slit. In another branch, it went through the right slit. There is no collapse, no randomness at the fundamental level, only branching. Every quantum event that has two possible outcomes splits the universe into two. The number of branches grows incomprehensibly fast. You're in one branch right now, and there are versions of you in branches you will never access, where every possible outcome of every quantum event in your life happened differently. Many worlds solves the measurement problem by removing collapse entirely. Everything is just wave functions evolving according to the Schrödinger equation. But it raises a different problem. Where do probabilities come from? If all outcomes happen, why do we observe some outcomes more often than others? This is called the probability problem of many worlds, and it remains unsolved. There's also the ontological cost. Many worlds is arguably the most conservative interpretation mathematically, because it takes the equations literally without adding any collapse rule. But the physical cost is astronomical. You must accept that the universe is constantly and irrevocably branching into an inconceivable number of copies of itself. Every radioactive decay, every photon interaction, every quantum event anywhere in the cosmos splits the branch. David Deutsch, a physicist at Oxford and one of the pioneers of quantum computing, is a committed defender of many worlds. He argues it is the only interpretation that takes physics seriously. Critics argue it is profligate to the point of madness. The third interpretation is called cubism, short for quantum Bayesianism, developed by physicist Christopher Fuchs and colleagues beginning in 2001. Cubism, says the quantum state, is not a description of what the particle is doing out there in the world. It is a description of an agent's beliefs about what they will observe. The wave function is not real. It is a user's manual for updating beliefs. When you measure a particle and the wave function collapses, nothing physically happened to the particle. Your beliefs updated. Cubism eliminates the measurement problem by saying there is no objective quantum reality to describe. There are only observers and their predictions. This sounds like philosophy rather than physics, but cubism is not alone in placing the observer at the center. Relational quantum mechanics, developed by Carlo Rovelli, holds that every fact about a quantum system is relational, real relative to a specific observer, non-existent from any view from nowhere. Israeli physicist Asher Paris, one of the founders of quantum information theory, stated it directly. Unperformed experiments have no results. That quote is cited in a Science magazine article marking the 100th anniversary of quantum mechanics, published in 2025. In 2025, on the island of Helgoland off the northern coast of Germany, more than 300 of the world's leading physicists gathered to mark the centenary of quantum mechanics. Helgoland is significant. Werner Heisenberg went there in 1925, alone, suffering from hay fever, stripped of distractions, and worked out the first complete mathematical formulation of quantum mechanics in a few days. 100 years later, in 2025, the same island hosted a reunion of the discipline Heisenberg founded. Standing out among the attendees were Carlo Rovelli, an Italian physicist known for relational quantum mechanics, and Christopher Fuchs of Cubism. According to a report published later that year, the two argued, as they have for years, about what the quantum equations actually describe. Everyone at that conference agreed on the math. Nobody agreed on what the math means. Now pause on that. 100 years. The equations pass every experimental test. Technology built on those equations, transistors, lasers, MRI machines, atomic clocks, runs the modern world. And the people who understand those equations best cannot agree on whether the moon exists when nobody looks at it. If you're still watching, drop a comment with your city and tell us which interpretation you find most convincing. And if you value research like this that goes all the way to the primary sources, subscribing is the most direct way to support it. Now back to the deepest part of the problem. That question is not rhetorical. It is exactly what the Wigner's friend thought experiment asks. Physicist Eugene Wigner posed this in 1961. Imagine a completely sealed, isolated laboratory. Your friend Gemena is inside with a quantum particle in superposition. She measures it. From her perspective, the wave function collapses. She gets a definite result. She knows the particle is here and not there. Now you are outside the lab. You cannot see in. According to quantum mechanics, you must describe the entire contents of that sealed lab, including Gemena, including her measurement result, including her memory of the result, as a quantum system that has not yet collapsed. From your perspective, Gemena is in a superposition of having seen result A and having seen result B. She is, from your perspective, in the same situation as Schrodinger's cat. When Gemena opens the door and tells you the result, from your perspective, that is when the collapse happens. But Gemena experienced the collapse the moment she looked at the particle. Two observers, two collapses, at different moments. Which one is real? In 2016, Daniela Frauschiger and Renato Renner extended this thought experiment into what is now called the extended Wigner's friend scenario. They showed, using standard quantum mechanics, that if you allow quantum mechanics to apply to everything, including observers and their memories, then two different observers following the same quantum rules can reach logically contradictory conclusions about the same event, not just different perspectives on the same event. Contradictory predictions about observable facts. This is not a thought experiment that sits safely in philosophy. Experimental teams have been working toward testing Wigner's friend scenarios with real quantum systems. According to a report in Quantum Zeitgeist from July 2025, researchers have already simulated the Wigner's friend system using 3 pairs of entangled photons, and the results show what the theory predicts: observer dependence. Depending on which observer's perspective you take, different facts hold. The experiments that would use artificial intelligence agents running on quantum computers as the observers to test this at greater scale are being planned. This is where a second crucial concept enters: relational quantum mechanics, developed by Carlo Rovelli in the 1990s. Rovelli's version says quantum states are always relational. They describe the state of a system relative to a specific observer. There is no absolute state. There's no view from nowhere. Gemena's observation establishes a fact relative to Gemena. Your description of the lab, as still in superposition, establishes a different set of facts relative to you. Both descriptions are complete and correct within their relational contexts. Reality, in this view, is not a single objective narrative. It is a web of observer-dependent relational facts without a unified story tying them together. Now stack on top of that the delayed choice experiment. John Archibald Wheeler proposed this in 1978 and elaborated it in 1984. Imagine you can fire a photon and then decide, after the photon has already passed through the double slit and is in flight toward the detector, whether to measure it as a wave or as a particle. You delay the choice of measurement basis until the photon is committed to its trajectory. The experiment was finally realized in a lab by Vincent Jacques and colleagues in 2007, published in Science magazine. The result: it does not matter when you make the choice. If you choose to measure which path the photon took, it behaves like a particle. If you choose to see the interference pattern, it behaves like a wave, even if you make the choice after the photon is already in flight. Wheeler said, "We decide what the photon shall have done after it has already done it." That quote is in his essay, Law Without Law, published in the book Quantum Theory and Measurement. The cosmic version of this experiment uses light from a distant quasar bent by a galaxy acting as a gravitational lens. The photon has been traveling for billions of years. Our choice of how to measure it when it arrives, right now, on Earth, in the present, determines what we say it was doing for those billions of years. To be precise, physicists like Sean Carroll and the authors of a 2024 paper in Quantum Studies, Mathematics and Foundations argue that delayed choice experiments do not require retrocausality, meaning causation running backward in time to explain their results. Standard quantum mechanics describes them correctly without any information traveling from future to past. The confusion comes from assuming the particle had a definite classical path before measurement. It did not. The superposition persisted the whole time. The delayed measurement did not change the past. It determined what we can now say about the past. But that distinction itself is deeply strange. If what we can say about the past is determined by what we choose to measure in the present, then what does it mean for the past to have been objective? Wheeler's answer was participatory universe. He spent the last decades of his life arguing that the universe does not simply exist. It is brought into existence through observation and participation. He coined the phrase it, from bit, every particle, every field of force, even the space-time continuum itself derives its function, its meaning, its very existence from answers to yes or no questions posed by physical apparatus. Things, the whole universe, derive their existence from registration of information. Wheeler developed this idea over decades, first presenting versions of it in the 1970s, and refining it through his retirement from Princeton in 1986. He was not a mystic. He was the man who worked alongside Einstein at the Institute for Advanced Study in Princeton, who coined the term black hole at a 1967 conference in New York, who calculated the physics of nuclear fission alongside Niels Bohr in 1939. When a physicist of that resume says the universe may not exist except as a result of information registered through observation, you do not dismiss it. You ask what it means. That is not a pop science claim. Wheeler is the physicist who coined the term black hole, who taught Richard Feynman at Princeton, who worked on the Manhattan Project at Los Alamos, who was one of the most rigorous and decorated physicists of the 20th century. It from bit is his considered conclusion from a lifetime of work. And here, in 2025, the International Year of Quantum Science and Technology, as declared by the United Nations, the scientific community is taking stock of where 100 years of this theory has left us. The math has never failed. Not once in 100 years. Every prediction, including probabilities of outcomes down to 10 decimal places, has held. The technology works. Quantum cryptography now protects communications in multiple countries. Quantum computers are being built by Google, IBM, and others. The equations are solid. But ask physicists what those equations describe, and you get at least 4 incompatible answers. A universe that is objectively real but fundamentally non-local, as the Bell tests imply. A universe that branches into all possible outcomes at every quantum event, as Many Worlds claims. A universe that literally does not have definite properties until observed, as Copenhagen implies. Or a universe in which quantum states are not descriptions of reality at all, but are descriptions of the beliefs of agents embedded within reality, as Cubism maintains. In May 2025, a paper published in Nature Communications showed that the loophole-free violations of Bell inequalities do not just rule out local hidden variables, they rule out entire classes of models that allow partial non-locality, partial retrocausation, or partially constrained freedom of choice. If any one of the assumptions underlying local realism fails, the paper proves it must fail completely. There are no halfway houses, no general alternatives. The universe is either local and realist, which the experiments have now ruled out to over 100 decimal places of statistical certainty, or it is deeply, radically, completely different from what our intuitions say. And then, in February of 2026, a physicist published a claim in a report covered by Earth.com that the universe is not empty space between galaxies and particles, but is rather a viscous fluid, and that this fluid causes the expansion of the universe. This claim is contested and requires much more evidence before it enters mainstream physics. But it is illustrative of where the field is. The foundational questions are still open, and researchers are still proposing radical revisions to what the universe is made of at its most basic level. 100 years after Heisenberg on Helgoland, the structure of reality is not a closed question. Here is the part nobody talks about at the level it deserves. The quantum shadow over reality is not about the strangeness of small things. Electrons and photons are small. Their weirdness could in principle be quarantined at the microscopic level. But entanglement does not stay small. In 2013, a quantum interference experiment was successfully performed with molecules comprising 810 atoms. By 2019, the record was 2,000 atoms in a single molecule. By 2025, MIT ran the double-slit experiment with atoms used as the slits themselves, confirming wave-particle duality holds even when quantum atomic correlations, not any spring or mechanical constraint, are what define the quantum behavior. The record for size keeps rising. There is no obvious wall where the quantum stops and the classical begins. This is the measurement problem in its most brutal form. Every object in the world is made of quantum particles. Every particle, as far as experiments show, exists in superposition until measured. But you do not walk around in superposition. Your coffee cup is where you left it. The laws that govern the particles seem to be profoundly different from the laws that govern the objects made of those particles. Nobody has a full account of why. Decoherence, the process by which quantum systems entangle with their environments and effectively lose their quantum character, explains a great deal about why we do not observe superpositions at everyday scales. When a particle interacts with even a single air molecule, information about its state leaks into the environment. The environment, containing trillions of particles, becomes entangled with the system. The quantum interference between different states gets scrambled by this environmental noise faster than any detector can register it. For a dust grain floating in air, this decoherence happens in roughly 10 to the power of negative 31 seconds. That is why dust grains look classical. The quantum information gets absorbed into the environment nearly instantaneously. But decoherence does not by itself solve the measurement problem. It does not explain why you observe one definite outcome rather than another. In many worlds, you observe both in different branches. In Copenhagen, the question is not allowed. In cubism, the question assumes an objective reality that does not exist. Michel de Vorey, the winner of the 2025 Nobel Prize in Physics, inventor of macroscopic quantum effects and superconducting circuits, publicly acknowledged that the cubist reconstruction of quantum equations directly inspired quantum experiments he designed. The quantum interpretation problem is not academic. It shapes which experiments get run and which technologies get built. Now for the late reveal. And it will reframe everything you just heard. In the 2015 Delft University Bell test, the team performed their loophole-free experiment by entangling electron spins in nitrogen vacancy centers embedded in diamonds. These nitrogen vacancy centers are defects in the diamond crystal lattice, places where a nitrogen atom sits, where a carbon atom should be next to an empty lattice site. The electron spin trapped at this defect can be prepared, manipulated, and measured with remarkable precision. The two diamonds were separated by 1.3 kilometers, with the measurements on each end made fast enough that light could not carry any signal between them within the measurement window. That is what closes the locality loophole. The specific number of trials was 245. That is all. From 245 trials, using a result with statistical margin p equals 0.039, the first loophole-free proof that local realism is wrong was established. A conclusion about the fundamental nature of reality, derived from 245 events measured in two buildings 1.3 kilometers apart in Delft, Netherlands. 245 trials, 1.3 kilometers. Electron spins in diamonds. That is the margin by which we know the universe is not locally real. And now the thing that makes this final fact cold. Niels Bohr said in 1927 that asking what a particle is doing when you are not looking at it is not a meaningful question. Werner Heisenberg agreed. They spent decades saying that the question was outside the domain of physics. Einstein spent the last 30 years of his life disagreeing, certain there was a deeper, local, deterministic reality underneath quantum mechanics, certain there were hidden variables giving particles their preset values. Einstein died in Princeton in 1955, 11 years before Bell published his theorem, 50 years before the first loophole-free test, 70 years before those tests reached 100 decimal places of statistical certainty. Einstein was wrong. The universe does not have definite properties when nobody looks. Or if it does, those properties are not local. And the two options, no definite properties at all, or definite properties that are instantly correlated across arbitrary distances without any signal between them, are both options that Einstein would have called unacceptable. The table in your kitchen is made of particles that, at their level, do not have definite positions until observed. The electrons in those atoms exist in probability clouds described by wave functions. The atoms themselves have been shown to produce interference patterns when fired through double slits. The wall between the quantum and the classical is not a wall. It is a fog that gets denser as things get bigger, and nobody knows exactly where the fog becomes solid ground. The shadow quantum mechanics casts on reality is not a dark corner at the edges of physics. It is cast directly on the center, on the question of what exists, on the question of what it means for something to be real when no one is looking, on the question of whether the word real means anything at all without specifying real for whom and from which perspective. 100 years of the most successful scientific theory in human history. And the answer to the question it raises about reality is still, we do not know. The interference fringes are still there every time you do not look.